Hello, we are recording a lesson on polarity and IMX. We, just like with several things in this unit, are not going in great depth. We're just going to barely scratch the surface of a few things. And so let's go over some basic stuff real quick about polarity. Alright. Polarity. First thing, if your Lewis structure has any lone pairs, then you have a dipole. It's called a dipole moment. We just say dipole for short, but it's technically a dipole moment. Alright, so if you have lone pairs, it doesn't matter where the lone pairs are. They don't have to be on the central atom. They can be on the terminal atom. But if you have dipoles in your molecule, if you have lone pairs in your molecule, then your molecule experiences something called a dipole moment. Now, when the dipoles or the dipole moment cancels out, then your molecule is called non-polar. Now this happens a lot when we have symmetrical molecules. So if there's symmetry, then the dipoles typically cancel out. Now if, put a bullet mark there and here, if the dipoles do not cancel out, then the molecule is polar. Well, that seems pretty simple, but being able to see how things cancel versus not canceling can be a little bit tricky. Alright, so let's look at a couple of Lewis structures real quick. So if we're going to be answering the question, is your molecule polar or not? Let's say we have something like CH4. Okay, it looks like this. Are there any lone pairs? Is question number 1. The answer is no. There are no lone pairs. If there are no lone pairs, that means it has 0. Hold on, the pen stopped working. There we go. We have 0 dipole moments. If you have 0 dipole moments, you are automatically, therefore, you are automatically nonpolar. There we go. Simple enough. Now, let's take a look at a couple more. Let's change this from CH4 into like CCl4. Like this. Alright, so question number 1. Are there any lone pairs anywhere in this molecule? The answer is yes. That means we have dipoles, or dipole moments. So now the next question is it polar? Well, let's see. Sorry, I'm back. Is it polar? Alright, well here we go. First of all, when we draw a dipole, is an arrow with a little crosshatch on the back of the tail. Alright, it points from the positive region to the negative region. And it should be pretty easy to know that because this little cross thing that you put on the back of it, it looks like a plus sign. Alright, so it's from the positive region to the negative region. Alright, well if you were looking at this molecule, you have to look at it. The dipole is going to go between two atoms. So there's two. Alright, I have the carbon and the Cl. Cl has all of these lone pairs on top of or around it. So that makes it the negative region, where carbon doesn't have any lone pairs on it. Alright, so since carbon doesn't have any lone pairs, that means that he is going to be the positive region. And so the dipole is going to go this way. Carbon is the positive region, that's where it gets the plus, and it points to the negative. Alright, now, here, points towards the negative lone pairs. Lone pairs are negative. There happen to be 3 sets of lone pairs, although it doesn't matter, it could be just one set. You're going to point towards the lone pairs of electrons, always. Alright, now think of these in terms of, you want to get your dipoles in your x, y plane, because if you do, then you'll be able to see how things cancel out a whole lot easier. So if you take a look, you think in terms of x and y, positive x, negative x. These two cancel. Then I've got, oh, not green, there we go. I've got a positive y and a negative y. These two cancel. Since all of the dipoles cancel, that means that this guy is non-polar. Alright, cool. Now let's take a look at this guy. Let's say I have NH3. Ew. Yep. There we go. NH3, right here. Okay, do I have lone pairs? Yes, I do. That means I have a dipole. So lone pairs. Yes. Therefore, I have a dipole. Now, the next question is it polar? It's only going to be if those dipoles don't cancel. Alright, so I have one going this way from this, these two atoms. There's one this way, pointing to those lone pairs, and this way. Alright, pointing that way. So let me get rid of the circle so you can see a little bit better. Alright, so I have these 3. They're all pointing in the same direction. Now I have this one that is straight up positive in the y. Real easy to see that. However, these other 2 are not both positive in the y. They're kind of like pointing at angles. So what you need to do is sort of imagine if you take these 2 arrows and average them together. Put them together. Alright, so if we put them together, or average them, take a look at them. Sometimes you guys need to look at it in terms of math. This green arrow, let's do that one in green. The green arrow is pointing in the positive x, and the positive y direction. Right? And then the arrow that's written in black is moving in the negative x and the positive y direction. Alright, well, these 2 are going to cancel each other out. You have a positive x and a negative x. So now, you basically have these 2, when they sum up, will sum up to give you an arrow that points straight up in the positive y. Because, after the x's cancel, that's all you've got left is this positive y. Now, I have this positive y arrow up, this other positive y arrow up. They're both pointing up. So if they both point up, then they don't cancel. So in order to cancel, one's got to go up and one's got to go down. So since they both are pointing in the same direction, they do not cancel. So the answer is yes. It polar. Okay. I want y'all to practice drawing and trying to figure that out. There's more to it, but just for starters, we'll start with that. The very last thing I want to talk about are your intermolecular forces. This could go on forever, but I'm going to try to make it really quick. The first one I have is hydrogen bonding. Number one, this is not a bond. As it says in your notes, this is an attraction between a hydrogen from one atom and either nitrogen, oxygen, or fluorine in another atom. Alright, this IMF stands for intermolecular forces. Hydrogen bonding is the strongest type that you can have. Alright, so number one, you have to have a molecule that has a hydrogen on it. So, like, let's do water. Okay, first of all, here is a hydrogen. It happens to be bonded to this oxygen, but it is not experiencing hydrogen bonding within itself. Because intermolecular forces means between two different molecules. Now, if I throw in another water molecule, like this, alright, so the interaction that's going to happen is we know that this is a negative region of this water molecule. This hydrogen out here by itself is a positive region. Alright, so this guy's positive over here, this is negative. Alright, so the attraction between these two, the positive and the negative, sort of like the magnets that we've been talking about, the attraction between these guys is represented like this, with these dots, saying that this positive hydrogen is attracted to this negative oxygen. This is a hydrogen bond. Alright, so it will only happen when you have a molecule that has a hydrogen bonded to it, and the hydrogen's attraction will only be with nitrogen, oxygen, and fluorine of a different, not the same, different molecule. Alright, so this doesn't happen too often. You don't really have hydrogen bonding as one of your normal IMFs, but you might. Alright, so that's the first one. The second one is dipole-dipole. It's hyphen dipole-dipole because it's showing between two different molecules. Basically, if you have a polar molecule, your IMFs are dipole-dipole. I'm not going into anything else more specific than that. Alright, number 3, London dispersion forces. Also known as LDF. LDF, if you have a non-polar molecule, it experiences London dispersion forces. Now actually, all molecules experience London dispersion forces. But at this point in time, a lot of texts and test banks and stuff don't recognize that for including polar molecules. AP does, so watch out for those of you that go on to take AP. But basically, when you are predicting your IMFs, if your molecule is nonpolar, then it's IMFs or LDF, London dispersion forces. If your molecule is polar, then you have dipole-dipole. Also, if it's polar, go check and see if you have a hydrogen, because you're going to have hydrogen bonding going on. And if so, see if this scenario works out, and you can have more, you will have more than one type. You can have 2 and 3.